Hello and welcome to this new session on G-Virtual X-ray. This time we're going to look at some theory about X-ray attenuation, and in particular we'll consider the Beer-Lambert Law. So photons, which is light, cross matter, and during its path a photon can go through the material without any interaction. So they reach the detector in a straight line. Sometimes photons will be stopped within the matter, and in that case, well, they are absorbed. Sometimes the path of the photon is changed, so we say that the photon is being scattered. And sometimes the photon is scattered and absorbed. For most X-ray imaging modalities, only directly transmitted photons are essential. So the ones that travel following a straight line, like these ones. And in many cases, the ones that are absorbed or scattered are not very useful. And what does that mean for us is that we could possibly ignore them. The way we compute the number of photons that have reached a detector following a straight line, so directly transmitted photons, so this is computed using the Beer-Lambert Law. So N in is the number of photons at a given energy. For here we have an object made of different materials of different thickness. That's the LP for the thickness. And the property of the material is given using the linear attenuation coefficient, known as mu. And mu will depend on the energy, the density of the material, and what it's made of, so the atomic number of the object material. And we just need to compute this equation. And the energy received by the detector will be the number of photons that have reached the detector multiplied by that energy. And this is what we simulate when we simulate an X-ray image. This is a number we want to compute. So we looked at the monochromatic case when there is only one energy. And here is, for example, our objects that we simulate, so a cube in which we inserted a cylinder. So the cube is made of soft tissue and the cylinder is made of bone in that example. And we know the thickness of how deep is the cube and the diameter of the cylinder. If we know the material properties, we can then compute the energies that would reach a detector. We just have to solve this equation. So here is what we do by hand. The energy is 80 keV or 0.08 MeV, and for each material, for each object, we compute minus mu times the thickness that has been crossed. And in that case, we will have 2.80 as a power of 0.002. If we were to consider a polychromatic case, in that case we need to iterate through all the energies present in the incident beam. So here we have this extra sum to go through all the energies. And basically we do the same as previously, but we have a for loop. So here is the same case, and if we have 3 different energies, 100 keV, 200 keV, 300 keV, here different numbers of photons, tissue material properties at different energies, so 100 keV, 200 keV, 300 keV, and we just need to solve that equation. So energy for 100K we got 10 photons, and mu for that material is this, the thickness is this. For the other material this is linear attenuation coefficient, the thickness, and we do it for the two other energies, and this is what the energy that has reached the detector. Now we're going to look at how it can be implemented using OpenGL.